the second video of Chapter 4, we're going to be examining two different types of experimental designs that are specialized, and they are called a matched pairs and a block design. In the previous video, we talked about the completely randomized design, the CRD, and that was basically like taking a simple random sample that we randomly assign individuals to treatment groups, and we give them the treatments, and in the end we compared how the two groups did against each other. And if one group showed a significant difference compared to the other one, we called our results statistically significant. So the other two things we're going to discuss are a much more specialized version of an experiment. So they're kind of similar to the idea of having a stratified random sample or a cluster sample, that they were more in-depth and more precise ways of taking a sample. So first, let's look at the idea behind a matched pairs experiment. So here's our main information right up here at the top. A matched pairs experimental design takes two forms. The experimental units are matched to produce more precise results than simple randomization. Or number two, each experimental unit receives both treatments and is compared to him or herself. Now, hopefully you understand the idea behind number two. For example, if we wanted to test out what could we test here? Two different types of diets. We could put you on diet A for 6 months, and then put you on diet B for 6 months. And then we could measure, how much weight did you lose on diet A versus diet B? If they were about the same weight loss, we'd say, well, there really is no difference between the two diets. If one diet produced greater results than another diet, we could say, hey, this diet definitely worked better for you than it did for maybe other people. Now, the first one where they said the experimental units are matched to produce more precise results than simple randomization. What that means is we have, say, two individuals, you and someone pretty similar to you in terms of specific characteristics, and it depends on the context of the problem. So for example, if we were talking about weight loss, we would want to match someone that is about the same build, about the same height and weight, and maybe what other factors you would consider with weight loss, maybe activity like exercise level. You don't want to have someone that exercises a lot matched up with someone that doesn't really exercise a lot, because that could be a lurking variable, the amount of exercise, because it differs. So you'd want to have two people that are maybe about the same height, about the same weight, and they exercise about the same amount as each other. And then we could give one of those people diet A and the other person diet B. And that way we could compare them to each other like they're kind of like the same person, but they're really not the same person. So the type of match pairs design you'll see more of will be more of this second one, where we're going to take each person, and each person will get multiple treatments, and then we'll just compare each person to him or herself. So we're going to look at a couple of examples here. All right, second example says an expert on worker performance is interested in the effect of room temperature on the performance of tasks requiring manual dexterity. Manual dexterity is another word for working with your hands. She chooses temperatures of 70 degrees and 90 degrees as treatments. The response variable is the number of correct insertions during a 30-minute period in a peg and hole apparatus. That's just a fancy word for like a children's toy of putting pegs in a hole. Yeah, it sounds complicated, I know. That requires the use of both hands simultaneously. Each subject is trained on the apparatus and asked to make as many insertions as possible in 30 minutes of continuous effort. So imagine using both your left and right hands, picking up pegs, if you will, probably cylindrical or rectangular prism-shaped pegs, and putting them into holes. Left and right hands nonstop for 30 minutes. All right, and we have two different temperatures here. You're going to be in a room at 70 degrees and a room at 90 degrees. And you can probably already think that probably people that are going to be in the 90-degree room are going to be more uncomfortable, and they're probably not going to work as fast because they're hot. And people in the 70-degree room are probably going to do more insertions correctly because it's a cooler temperature. They can probably relax more, And that's the result that we would expect to probably see. Does that mean that's what we will see? Not necessarily. So part A says outline a completely randomized design. This is what we talked about in the previous video. Okay, so we're going to have our 20 subjects. We're going to randomly split them up into two groups of 10 people each. And within each group, let's say group 1, we give the 70-degree room, and group 2, we give the 90-degree room. So after our 30 minutes at 70 and 30 minutes at 90 degrees, we come back and we compare the number of correct insertions. If, say, the 70-degree room has a significant amount more of correct insertions than the 90-degree room, we would say that our results are statistically significant, that there was a definite difference. If the two numbers here for correct insertions are pretty close to each other, and we can't say that there is a definite difference between the 70 and the 90-degree room, then we would say our results are not statistically significant, that there was no big difference between the two treatments. Now for B here, it says, because individuals differ greatly in dexterity, the wide variation in individual scores may hide the systematic effect of temperature, unless there are many subjects in each group. I mean, we can't really get very specific results to apply to the whole population if we're only putting 10 people in each temperature room here. 10 people is not a big enough sample size, if you will. Okay? So it says, describe in detail the design of a matched pairs experiment in which each subject serves as his or her own control. Okay, so instead of just 10 people getting one treatment, we're going to say 10 people get both treatments. Okay, so we're going to start with our random assignment. We're still going to split them up into two groups of 10. And so now at this point, we may say, all right, let's flip a coin. Let's keep this completely random here. If heads comes up, group 1 starts off with the 70-degree room. If tails comes up, group 1 starts off with the 90-degree room. So let's say heads comes up. So we start off group 1, and I randomly decided that they would get the 70-degree room and group 2 would get the opposite. And then after a certain amount of time, not just 30 minutes and then let's start the next 30 minutes, but I put these people in the 70 and 90-degree rooms for 30 minutes, give them a couple hours break, get them to relax, get them fresh to where they were when they first started the first treatment. And now we switch them. The people in the 70-degree room we put in the 90-degree room for 30 more minutes, and the people in the 90-degree room then go to the 70-degree room. So any difference in temperature should be canceled out here, because technically both of our groups of people have been given both treatments, just in opposite order. And then we come together and compare how many more correct insertions were made in the 70-degree room than the 90-degree room. Okay, so the reason why we do it kind of opposite here is, if people are in the 70-degree room and then go to the 90, there might be a difference between them starting out in the 90 and then going to the 70. If the people were in the 90-degree room first and they felt very stressed and just hot and overwhelmed, and then they go to the 70-degree room and they're like, oh my gosh, this feels fantastic in here. I can work twice as fast as maybe I was in the 90-degree room. Versus if people already started out in the 70-degree room and that's what they expect, maybe they didn't work twice as fast because they weren't subjected to an extreme 90-degree heat in a room. And then when they go to the 90, then they're very overwhelmed. And obviously work production may slow down significantly then. So there is a difference between our two groups, between starting out in the hot room or the cooler room. So that's the main idea behind a matched pairs design, is that pretty much each subject gets subjected to multiple treatments. And then we just compare each person to him or herself between all the treatments. Now the other type of idea is called a block design. And this is going to sound really familiar because a block design is kind of like a stratified random sample. But there's a big difference here. A stratified random sample deals with sampling, with selecting people. A block design is a type of experiment. It's not how you are selecting the people. So they are very similar to each other, but there's that key difference of sampling versus experimenting. Okay? So it says a block is a group of experimental units or subjects that are known before the experiment to be similar in some way that is expected to affect the response. In a block design, the random assignment of the units to the treatments is carried out separately within each block. So when you look at a block design itself, it looks like you're doing the experiment multiple times within each block, within each strata, if you want to kind of think of it that way. So again, instead of stratas, we have blocks. So the first example here says the progress of a type of cancer differs in men and women. A clinical experiment to compare 3 therapies for this cancer therefore treats sex as a blocking variable. If men respond differently than women, then we obviously want to separate men from women to see if men respond differently to a certain therapy than women may respond differently to a different therapy. 2 separate randomizations are done, one assigning the female subjects to the treatments and the other assigning the male subjects. Note that there is no randomization in making up the blocks. The blocks are made by gender. The randomization comes into play when they split each gender up into the 3 treatments. Okay, so typically when we start to split up our groups in a completely randomized design and in a matched pairs design, the first thing we do is the random assignment. But notice here are all of our subjects. First we split them up into the blocks, men versus women. And then once we have all our men together, now we randomly split them up into groups. And the same thing for the women down here. Once we have all the women together, then we randomly put them into groups. Okay? Again, you're not going to do the random assignment at first. It's not like you're randomly putting all the men together and all the women together. That makes no sense that you randomly do that. You're just saying all men over here, all women over there. Now let's introduce randomization to this. So this says, label the main features of the randomized block design. Well, I've already got the picture set up here. And we're just going to label where does the randomization come into play, then the groups, the treatments, etc. It says list the group sizes. There are 180 subjects total, 30% of whom are male. Okay, so number 1, we have our 180 subjects here. Now, how many men and how many women do we have? It's not 90 and 90 because they didn't say 50% are male. It said 30% are male. So if I have 180 subjects and 30% of them are male, well, that gives me 54 men. And if I have 54 men, then I have 126 left over out of my 180 that must be women. So here are my blocks that I've split up because it says 2 different types, or a type of cancer differs in men and women. Therefore, I'm splitting up my blocks by gender. So there's my 54 and 126. Now from there, I randomly split up my 54 men among 3 treatments. So 54 divided by 3 is 18 per group for the men. 126 divided by 3 gives me 42 in each group for the women. Is it okay that there aren't as many men as there are women? That's fine. Okay, in real life, it's going to be nearly impossible to have 50-50 or even amounts of individuals per group or per block. That's very rarely going to happen realistically. Okay, so then my group 1 random assignment of men, they're going to get therapy 1, group 2 gets therapy 2, group 3 gets therapy 3. And in the end, I go and look at, well, let's look at survival rates after these therapies. How many men, what percentage of men survived after getting therapy 1? How many against therapy 2? How many at the end of therapy 3? And then I can decide for men which therapy did best. Okay, maybe therapy 1 was the winner for men, that we had more men survive with therapy 1 than 2 or 3. And then I come down here for the women, and I do the same thing with my 42 groups of 3 sets of women here, and I give them therapies 1, 2, and 3, the same therapies 1, 2, and 3 as I did for the men. But maybe therapy 3 ends up being the best therapy for women. More women survived with therapy 3 than 1 or 2. Okay, and this is why I decided to split my genders, because I had a feeling before the experiment started that men might respond differently than women. Now, let's say you do this whole experiment, but you don't split up by gender, and you just take your 180 subjects and you split them up into 60, 60, and 60 for therapies 1, 2, and 3. Well, then you might not find the same result. Okay, maybe therapy 2 ends up being the winner for men and women combined. So there's that lurking variable of gender that we have ignored. And then if you go, wait, maybe men and women will respond differently. But if you've already done the experiment, you can't at that point go back and say, well, I should have done this. That's not block design anymore. You have to knowingly know before the experiment that there's going to be a difference between whatever variable that you're blocking by, whether it's gender or age or income level or education level. You have to block before you experiment. Otherwise, it's not really fair that you go back after the fact and then split them up. That's very unethical, if you will. Now, one thing that I see students do a lot of is they'll take the men survival rate and the women's survival rate, and then they come back and say, let's compare overall. Well, you don't want to do that overall. The main reason why we split them up into blocks is because we thought there was going to be a difference. So why would we then compare our two things as one at the very end? We don't want to compare our individual blocks at the very end. It really makes no sense. You're splitting them up at the beginning of the experiment because you know there's a difference. So it makes no sense to compare your different results at the very end of the experiment. That defeats the whole purpose of blocking to begin with. So there is no end comparison between all your blocks. You just leave them as separate blocks. So it looks like one big experiment that you are doing multiple times, one for each block. One last example. It says a preliminary study conducted at a medical center in St. Louis has shown that treatment with small, low-intensity magnets reduces the self-reported level of pain in polio patients. During each session, a patient rested on an examining table in the doctor's office while the magnets embedded in soft pads were strapped to the body at the site of pain. Sessions continued for several weeks, after which pain reduction was measured. A new study is being designed to investigate whether magnets also reduce pain in patients suffering herniated discs in the lower back. 100 male patients are available for the new study. So part A says, describe an appropriate design for this new study. Your discussion should briefly address the treatments used, methods of treatment assigned, and what variables should be measured. Okay, so it says we have 100 males. We're all going to test with pain in herniated disc in their lower back. But they give us no preconceived notion of maybe there's going to be a difference between maybe white patients and African American patients. They give us no idea behind that. So this is seeming like this will not be a block design. They're not telling us kind of beforehand we may consider splitting up our 100 males before giving them the treatments. So this is looking more just like a completely randomized design. So first, let's randomly assign our 100 male patients into two groups of 50 men. Okay, now our treatments. Well, obviously we're talking about magnets, but what would our second group of people get? We're going to have magnets and not magnets? Well, wouldn't the second group know they weren't being given magnets? Don't you think they'd be like, so where's my treatment? And they're going to go, oh, you don't get one. They're going to go, oh, so we're the control group. Well, I still feel the same amount of pain. That's awesome. So what's going to look like wins out in the end? Hey, the magnet group, because they're going to be like, oh yeah, that totally helped me out getting that treatment. So the other group won't get magnets, but we still have to make them believe that they are getting a treatment. So we are going to make the other group a control group, but we're going to put, I don't know, non-magnetized magnets in the soft pads that they're going to lay on. We still want them to believe that they're getting a treatment. Okay, so I have no magnet in soft pad, or we could put maybe faux magnet in soft pad, put a stone, something that makes them believe they're still getting some sort of treatment here. Okay, so this is essentially treatment 2 is my control group. Okay, because really people that are getting the magnet inside the soft pad, maybe they feel like, hey, I got better. My herniated disc in my lower back, the pain's gone away. Excellent, this really worked. But it could just have been a placebo effect. Just because they know they were receiving a treatment, maybe psychologically, miracle happened and the pain went away just because they thought they were getting an actual treatment. And maybe the magnet really isn't the best thing since sliced bread. People just thought it was going to be the next best thing since sliced bread. And then in the end, we can come back and compare pain relief. People that were really getting the treatment and people who thought they were getting the treatment. And if magnets really do make a difference, we should see that this group in treatment 1 saw a significant increase in the reduction of pain levels in their lower back. And then we could say that our results are statistically significant. If the difference between our two groups isn't very differentiated between each other, then we would say that our results are not statistically significant. And then part B says, would you modify your design if, instead of 100 male patients, there were 50 male and 50 female patients available for the study? If so, how would you modify the design, and if not, why? Well, we don't really know if males and females respond differently to magnets, so we might go out on a limb and say, maybe there will be some difference. Maybe, we don't really know. So why not go ahead and introduce a block design? And let's split up by gender. So let's say we have our subjects, 50 men and 50 women. And remember, we're not randomly putting them into 50 men and 50 women. They are being split, not randomly. And now we introduce our random assignment for the 50 men and the 50 women. So the 50 men get split up into 2 groups of 25, and the 50 women get split up randomly into 2 groups of 25. And then maybe group 1 of the men gets the magnets, group 2 gets the fake magnets. Same thing for the women. And in the end, we compare our men to each other, and we compare the women to each other. Again, there is no ultimate comparison at the very, very end. Okay? There is no other arrows leading down and say, let's compare overall. We are not going to do that. That's why we split them up to begin with. So that's it. It's kind of like one experiment, but there's 2 branches of it. And you cannot bring the branches back together in a tree. You never see a tree split off into 2 branches, and then somewhere down the line the branches are like, oh, hey, buddy, what's up? We were once together. Let's get back together as a new branch. And that is all for the second video and last video of Chapter 4.